Good morning, student. Today we want to find out the value of electric field due to a charge infinite plane sheet. And now this will be the third application of Gauss law. Here first topic we want to consider the one of the infinite plane sheet. Suppose here if we consider this will be the infinite plane sheet. Suppose this will be the one of the infinite plane sheet. First of here, meaning of infinite plane sheet means the length of this conductor, which is very high as compared to the width of the same plane sheet. So that's why that is called as the infinitely plane sheet. First of here, the shape of this sheet is uniform. That is, the shape of this conductor is uniform. So that's why the charge distribution on this sheet is also uniform. Suppose here, if we consider the n number of charges which is distributed on the surface of conductor is uniform. Suppose this will be the number of charges. Right? Here the shape of the conductor is uniform, so that's why the charge distribution is also uniform. And due to the uniform charge distribution, here the surface charge density is also uniform, that is a constant. Here the value of the surface charge density is, suppose here, Q upon A or Q upon ds. Right? Now this is the formula of surface charge density. Here capital Q means the total number of charges present on the surface of this conductor. And A means their total area of this conductor. Suppose here if we consider that area is there A. Here small q is the number of charges in a small area of this conductor. Suppose here if we consider this will be the small area of this conductor. Their area is there, suppose ds. Here the charge density inside this small area, which is also same, right? That is sigma, which is equal to the charge upon area ds. Then now here we want to take the 2 points. Suppose this will be the point P, this will be the point is P, and second point is backside of this plane sheet. Here this conducting plate, their thickness is very small, so that's why the effect of the charges which is produced on the both the side, that is the front side and back side of the sheet. For other one, suppose this will be the plane sheet and their thickness is, suppose some thickness of this conductor, then what happen at that time, the charges which is present on the front side of that conductor, then that charges produce the electric field only in one direction, right? But what happened here, the thickness is very small, so that's why the number of charges present on the surface of the conductor, so that charges produce the electric field in both the direction, that is the front directions and backward directions, right? And here the distance of point P from this sheet or from this small area, suppose that distance is there, how to get there, suppose that distance is there small r. If the distance of point P is r, then the distance of P dash, which is also r. It means that P and P dash at the same distance. Then here we want to draw the small Gaussian surface around the point P. Suppose here if you take this will be the Gaussian surface around the point P. Similarly, we want to draw the small Gaussian surface around the P dash also. And now, if we join these three areas, then here we get the one of the cylinder. And here, what happened here? Here this plane sheet, which is a passing the middle of the cylinder, just like that, right? So here the number of charges in the small area is Q and their area is ds, so that's why their surface charge density is sigma, and the distance of point P and P dash is the same. So that's why this number of charges which produce the electric field intensity at P and P dash, and their values are same. Again, this will be the positive charges, so that's why the direction of electric field, which is also outward directions. It means that at point P, the direction of electric field is outward, that is along this direction. And at P dash, the direction of electric field is, put it there. So this will be the direction of electric field at point P dash due to the number of charges present in the small area ds, or this whole conductor. Here, first of you know that. Now this will be the area is ds. Again, this will be the area is also ds. And you know that. If we want to draw the area vector to this small area ds, then their direction, which is also outward, because of the direction of area vector is perpendicular to the given area. So here the direction of electric field intensity and area vector is same. So that's why angle between the E and ds for this case, which is equal to the 0. Similarly about P dash. Here the direction of area vector, which is also in outward direction. Again here the direction of electric field and area vector is same, so that's why angle between them is 0, right? Here this cylinder represents the Gaussian cylinder, and now here to that cylinder, now this will be the two ends, this will be the first end, this will be the second end. Here the shape of these two ends are there circular, right? And the cross-sectional area of this one is ds. Again here also ds. Suppose here if we consider this will be the first surface of this Gaussian cylinder, this will be the second surface of the Gaussian cylinder, and now here we want to take the third area of the Gaussian cylinder. Here we get the three surfaces. This will be the first surface, this will be the second surface, and this curve one. Right, this is the curve surface, which is also the one of the surface of that Gaussian cylinder. Suppose here again if we consider that area is ds, then now here this one represents the direction of area vector. But for this point the direction of electric field intensity is outward. Here for the third case, suppose this will be the third case, right? For the third case, the angle between the E and ds is 90 degree. It means that for this case the angle is 90 degree. Then now here, using all this one, we want to find out the value of electrical flux. See here, the electrical flux passing through this Gaussian surface, which is equal to the Gaussian cylinder, which is equal to the, so phi, which is equal to the, what you get there, integration over the closed path, right? What you get there, vector E dot vector ds, right? Here this will be the symbol of integration, and now this will be the integration over the closed surface. Here this closed surface, which is a consist of three different surfaces. This will be the first surface, this will be the second surface, and third one is the curved surface, just like this one. Suppose here if we consider this will be the Gaussian cylinder, then to the cylinder this will be the first surface, right, which is circular. Again this will be the second one, again this will be the circular, and third one is their curved surface, right. So that's why this integration, which is written as into the three part. Now the integration for the first area, what we get there, E vector E dot vector ds. Similarly for the second area, that is second one, E dot ds, right, and again plus for the third one, that is for the third area, what we get there, vector E dot vector ds. Here again we want to write down this equation in terms of the magnitude. What we get there, therefore phi, which is equal to the integration for the first area, right, E ds cos theta, plus for the second one, right, what we get there, integration for the second area, E ds cos theta. And now for the third term, which is written as integration for the third area, that is the curved area, what we get there, E ds cos theta. See here what happened for the first area. Here the angle between the vector E and ds is 0 and the value of cos 0 is 1. It means that the value of this cos theta, which is equal to the 1. Again for the second area also the value of cos theta, which is equal to the 1, right. But for the third one, that is the third area, what happened here, the angle between the vector E and ds is 90 degree. So cos 90, which is equal to the 0. So that's why the value of this integration is 0, right. So here we write that angle, but theta, which is equal to the 0, then cos 0, which is equal to the 1. If second one, if theta, which is equal to the 90, then cos 90, which is equal to the 0, right. So using these values we want to write down this equation. What we get there, therefore phi, which is equal to the integration for the first one, E ds, plus integration for the second one, what we get there, E ds, plus for the third one is 0. We know that the distance of point P and P dash from this plane sheet is the same. So that's why at both the places the value of electric field is same. And you know that the rules of integration, we keep the all the constant quantity outside the integration sign. So what we get there, here E is constant, so what we get there, E integration for the first one, first area, that is a ds. Again here E is constant, so the integration for the second area, that is a ds, right. Here the value of E is constant, right. Why we write this E outside, because of the value of E at point P and P dash is same, so that's why we keep outside the integration sign. Now here the area of this Gaussian surface is the same at point P and P dash, right. Now this will be the smaller one, but suppose here if we want to find out the effect of this whole conductor, then at that time the integration of ds is nothing but the A, right. So that's why here we write here E into the A plus E into the A. Here the integration of ds, which is equal to the A, right. So what we get there, phi, which is equal to the EA plus EA, what we get there, 2EA, right. Suppose this will be the equation number 1. So this will be the value of electrical flux, through this area, that is a two area, that is from the point P and P dash. Now This is about the electrical flux from the geometry. Now again here we want to use the Gauss theorem. It means that we want to compare this equation with the Gauss theorem, and we know the equation of Gauss theorem or Gauss law. What you get there? As per Gauss law. Now phi, which is equal to the, here total charge is Q upon epsilon. Here epsilon represents the permittivity of a medium, right? But here the value of charge is, from this equation what we get there? Charge which is equal to the sigma into the A. Suppose that if we substitute that, what we get there? Sigma A upon epsilon, right? So this will be the statement of Gauss theorem. Suppose this will be the equation number 2. Here now if we see the equation 1 and 2, their LHS side is same. If their LHS side is same, then their RHS side which is also same. So that's why here we want to compare the equation 1 and 2. So what you get there? From equation 1 and 2, what you get here? Here 2EA, which is equal to the sigma A upon epsilon, right? So here what happened here? On the both the side we get the A, so that A get cancelled. Now we want to find out the value of electric field intensity, so rearranging this one. So what you get there? Finally here E which is equal to the sigma upon, now here we want to transfer it to this side. So what you get there? 2 epsilon. That is E which is equal to the sigma upon 2 epsilon. This will be the value of electric field intensity due to a charged infinite plane sheet.